Hi. In this video lecture, we want to talk about the fact that we can make the PIC operate at different frequencies. You heard me mention 7 times, several times, that the default oscillator frequency is 1 megahertz. When I call up configure USART, I use that frequency right here. I'm saying, look, this chip is working at 1 megahertz. Other frequencies are available. And they're available when you use these special function registers OscOn and OsTune. SFRs are like the tris and port SFRs that we've seen. You set the bits to do the functions you want. Okay, so let's look at these functions. I have them here. There's the chip. Here we go. Here's OscOn. And what we want to focus on are bits 6 to 4. These are the names of the bits. And it says I can go from 31 kilohertz up to 8 megahertz. So there's 1, 2, 3, 4, 5, 6, 7, 8 frequencies. There's a little note here, 3. That's the default frequency. So if I don't make any request, my chip operates at 1 megahertz. So that's perfect. But there's also this OsTune right here. And it says for OsTune bit 6, which is called PLLEN, it has a frequency multiplier. When it's set to 1, we have a turbo mode. And 4 megahertz and 8 megahertz will quadruple in speed to 16 and 32 megahertz. So besides the other 8, we can also be operating at 16 megahertz and 8 megahertz. Now, that's relatively complicated to do. You're not used to working with the special function registers very much. So back in the code, we've given you a little library called os.c and os.h. Let's look at os.c. Okay, so set oscillator to 1 megahertz. And here's OsCON bits and OsTune bits and the names of the bits. And we've chosen here 100 and PLN equals 0. 0 means don't try to use the doubling. It wouldn't work here because 100, if we go back here, is the default 1 megahertz. So it wouldn't work. So if we go to the program, we can actually make a second function. So let's copy this. Right. And let's make it, say, 16 megahertz. Okay. TOSC would be 1 over 16, which would be 1 over 16 microseconds. And this would be 1 over 4 microseconds. Okay. So 16 times faster. Let's name this consistently. And the settings we want, well, we know this guy needs to be turbo, so we set it. That's computerese for making it 1. And according to this table, we would want 4 megahertz times 4 is 16, so 110. So let's come back to this code. And this guy has to be set. So now it's 110. Great. That's all the code needed to do that. We do have to come here, and I'm jumping ahead a little, have to make the code for 16 megahertz, right? I have to have the prototype here. Then I go back to here and make sure I don't make any mistakes in the function name. I'm just going to copy it. Okay. And I want this to work, so I had to make sure I set this to 16 as well, right? Because this is a 16 megahertz, this needs to be 16 megahertz. If I put a different number here, I will not get proper communication. Let's build and load. Okay, and it's programming. And just as we wanted, we got a little hello world. That's all it took. It's that simple. What you're going to be doing for me is you're going to set up all the functions in os.c and os.h so we can go from the 31 kilohertz up to 32 megahertz. There are times when we're going to want to switch speed. Okay? The one thing that I'll emphasize again, if this is 16 megahertz, this has to be 16 megahertz. If I go back to 1 megahertz, I need to switch back to 1 megahertz. Let's go make sure that worked. Okay, you got the hello world. Might not look like it. You saw a little blink where it erased and rewrote it. Okay, that's it. Now there's another little thing that's kind of interesting. Suppose the communication wasn't working. Is it not working because of configure use cert or because I've done something wrong with this function? Well, there's a way to check if your PIC is running at the right speed. If we come up to configuration bits.h and you come down here, there's this pragma statement or directive saying that the oscillator setting is INTO IO7. And what that means is that the oscillator selection bits, the internal oscillator block, the clock out function is on RA6. What that means is we've set the PIC so that whatever speed it's operating, it outputs a square wave signal to pin RA6. Let's look at pin RA6. Let's find it. Got it here somewhere. Here's RA6. RA6 on our pin, on our chip, is pin 10. So here's RA6. And what it does is it does this behavior now, clock out. So it's going to tell us what the frequency is. Now it won't, if I'm running at 16 megahertz, it won't actually output a 16 megahertz signal. It will actually put out 16 divided by 4 megahertz. So whatever you read on an oscilloscope, and we will have you use an oscilloscope to check this, whatever setting you have, 4 times that oscillator, 4 times the reading on your oscilloscope will be the actual frequency. Right? So we need to remember that. RA6, whatever the frequency you measure, multiply it by 4, and that's your actual operating PIC frequency. I want to talk to you a little more about the configure use cert. Okay? And what this first number says, I want the communication speed through the USB serial pin to be at 9600 bits per second with my chip operating at 1 megahertz. You might recall that if we go to PuTTY and look at the settings, and down here serial, I've chose 9600. 96 is a very basic standard value. It's serial communication's been around for a long time. 9600 is sort of like the slowest speed. Well, it's not the slowest speed. You could go down to like 240 bits or characters per second. But it's a very safe one. Very many devices have it as their default speed. So if something's not working and you guess at 9600, probably you can establish communication with just about anything. But we could choose different numbers. With the little device we've given you, you can actually go up to something over 1,000,000 bits per second. And you say, hey, why don't I do that? My communication through PuTTY would be a lot faster. It's not quite that simple. This configure USART program has to do a calculation. And the idea of the calculation is to match the speed of the chip with the signal speed going out. If the signal speed you request is not necessarily the signal speed you actually get. So let's go to configure usart.c. Right? Here's this setup. Up here, it's a little hard to see it very well here. There's a bunch of statements, a function that's supplied that we're doing, but there's this formula in here. This formula is a number that we use so that we can calculate what number to use. So this formula says you want at 1 megahertz, you want 9600. This is the integer value that you use to get that speed. But it's not always an exact match for what you want. Okay, so let me call this back up. And I want to go to this calculation right here. This is the same formula that was in configure USART. It says take the oscillator speed that you're working at, divide it by the baud rate, like the 9600, and then divide it by 4. Since this is an integer, to make the rounding correct, we up it by 0.5. Because if this is an integer, this is a decimal calculation. So if it was 4.6 plus 0.5 would round it over, right? And then subtract 1. It's because of the way the formula works. Okay? So when we do this calculation, say at 1,000,000, right? The value of SPBRG that we get is 25. The exact value would be 25.54. But SPBRG can only be an integer. The actual baud rate we get out is 9615 bits per second. That's not exact. We don't worry about exact. We just had to be close enough. Serial communication is fairly forgiving as long as you're within a few percent. Call that maybe 5–10%. The communication should work well. If I want to work at other speeds, I would have to check that calculation and make sure it'll work. Here's a handy hint. 9600 should work for any speed you choose. Okay? But if you want to communicate at like 1,000,000 bits per second, you probably won't get that at all speeds. So, to emphasize, we have this formula. When you're trying to communicate over this USB to serial port, there's a bunch of things that could be wrong. Your program is wrong. The wiring on the PIC to the USB serial pin could be wrong. Your calculations might not be close enough. So when you're debugging serial communication, could be your wiring, maybe in your code these two frequencies don't match, or maybe the number you're trying to get doesn't come close enough to the 9600 or whatever it is that you're trying to get for the communication to work well. Usually a sign of that is you get garbage coming out. Right? And the last thing would be on your PuTTY, going back to the settings, is maybe the speed that PuTTY is set to is not the same as the one you're requesting. Right? So if you change in your program what speed, PuTTY has to change too.